Testing. Alright, intro to advanced wastewater treatment sequence of processes, polishing ponds, post-aeration, micro-straining, filterization, activated carbon absorption, phosphorus removal, land application system, nitrification, denitrification, three-stage biological system, anaerobic contact processes. This course is adapted to Unified Facility Criteria, United States Government, which is public domain authorized, unlimited, and is not copyrighted. Alright. Introduction to advanced wastewater treatment. The sequence of the treatment process throughout which wastewater passes, usually characterized as preliminary treatment, primary treatment, secondary treatment, tertiary treatment. Discussions is introduction of advanced treatment methods and process. Advanced treatment is primary with a tertiary treatment. A number of different unit operations are used with various configuration to make up an advanced wastewater treatment system. Particular situation determines the most applicable to process designs. General sequence units operation typically used with advanced treatment is presented with a scheme in the figure 1, table 1, presence of the application of the advantages and disadvantages of the various advanced wastewater treatment process arranged in such a way to provide a ready comparison between the alternative treatment processes. The application listed are those with which the processes are normally selected. However, many processes with all those selected on the basis of their effectiveness and removal of particular pollution obtain additional benefits in the control of the other waste characteristics. This is primary stage, mixing, colligation, clarification, secondary treatment, phosphorus removal, the valence of activated sludge, chemical addition, mixing, colligation, clarification, tertiary stage, phosphorus removal, the chemical addition, mixing, colligation, clarification, polishing, lagoon, post-aeration, filterization, carbon absorption, notification, activated to sludge, micro-straining, carbon absorption, membrane, nitrification, denitrification, air stripping, breakpoint, chlorination, selective and ion exchanger, lead to land treatment. And then over here it shows your description, physical units and chemical unit process, biological unit processes, your wastewater feed, the SS, BOD, COD, and nitrate, and NH3, or origin N, number 3, PO4, NO3, PO4, TDS, and waste of ultimate disposal. Alright, 3. Polishing ponds. Wastewater treatment ponds may be used with the economic method of upgrading existing secondary treatment facilities to obtain with involved improve organic suspended solids. Removal of both aerobic and anaerobic ponds can be used for this purpose. Ponds using polishing purpose for subjects to the same operating characteristics as those used in primary and secondary treatment, with the same precautionary design consideration must be applied. Post-aeration. This can be accomplished by the diffuse of the cascaded U-tube mechanical aeration. Diffuse aeration is carried out in 9 tanks 9 to 15 feet deep with a 10 feet to 50 foot wide depth of width, for the ratio maintained at least 2. Detention time of about 20 minutes. The maximum air requirement is approximately 0.15 cubic feet per gallon of wastewater treated. Mechanical aerated basins are 8 feet deep and they require 15 to 50 square feet per aerator. Surface aeration is most efficient. Mechanical aeration terms required horsepower 0.1 horsepower to per 1,000 gallons of the fluid. Drop required cascade aeration step weir count structure and ore and rapidly sloping channel filled with large rocks. Concrete block will depend on the desired oxygen uptake. 2 feet of the drop will provide each of the milligram per liter to dissolve oxygen increase required. Micro-straining. Description and process. Micro-straining consists of rotating a drum supporting very fine stainless steel with a plastic screen. Wastewater is fed into the side of the drum, filters radially outward through the screen. The mats of solid accumulation screen inside of the drum. The solids are flushed into the removal through the top of the drum pressurized backwash system. From this trough, the solids are returned to the head system. Process fluently. Wastewater can be used in blackwash for backwash. Table 2 provides performance data with several microscreens installations. Show the parameter typical value: hydraulic loading 23 micron fabric, 600 gallon square feet an hour, 35 micron fabric brick, 80 gallon per square feet. Backwash water required 3 to 6% average flow. Backwash pressure 15 to 50 psi. Drum speed 0.7 to 4.3 RPM. Allowable head loss 12 to 18 inches of water. Optimum hydraulic loss through screen 6 inches. Optimum solid loading 0.88 pounds a day square foot at 6.6 gallon per minute square foot. Our design factors. Micro strainers will design with a base width not exceeding 10 gallons per minute per square foot with a submerged screen area with a design maximum flow. The multiple units are provided. All the units were protected against freezing. Typical opening size with a micro straining fabric is 25 to 35 to 60 micron, respectively. Number of openings per square inch of 100 between being 165,000, 80,000, and 60,000. With 23 micron screen fabric, the micron strainer can be credited up to 75% of the solid removal. 60% of the removal is achievable using 35 micron fabric. Maximum solids loading for micron straining activated sludge fluent with 0.88 pounds per day per square foot at a hydraulic loading at 6.6 gallons per minute per square foot. Advantage efficiency. Advantage micro straining is relatively low head loss between 12 and 18 inches of the 6-inch limit across single screen efficiency. Micro strain is determined with the hydraulic solid loadings as well as filter characteristics of a fluent. Micro strainers will not remove colloidal material or small micron size algae. Micro strainers are also adversely affected fluctuation fluent composition quality. Hydraulic control. Hydraulic control micro screening units effective with the varying of the drum speed and proportional with the differential head across the screen. The controller is commonly set with a give of the peripheral drum speed of 15 feet per minute at 3 inches differential 125 to 150 feet per minute within 6 inches addition. Backwash flow rate pressure may be increased with a differential reach for the given level. The operating submergence is related to the fluent water level. The head loss through the fabric. Minimum drum submergence value for the given installation is level of the liquid inside of the drum with no flow over the fluent wear. Maximum drum submergency is fixed with a bypass wear, which permits flow when the excess unit capacity to be a bypass of the maximum submergency. The maximum drum differential should never exceed 15 inches. A fluent bypass wear should be designed as follows. Select drum submergence level of 77.5% of the drum diameter for no flow over the fluent wear. Locate the top of the fluent wear subject to the submersible level. Determine the maximum flow rate size of fluent with a wear limit. The liquid depth of the fluent chamber with above the wear 2 to 3 inches of the maximum flow rate. Position bypass the wear 9 to 11 inches above the wear with a 3-inch head on with the fluent wear maximum flow plus 6 to 8 inches differential drum on maximum drum speed and maximum flow. Size and bypass wear length to prevent length above the fluent wire flow exceeding 12 to 18 inches per maximum flow overflowing the top of the backwash collecting hopper. Backwashing. Backwash jets are directed against the outside of the microscreen drum as press passes highest point of rotation. All half of the flow of the penetrate fabric, dislodging the mass of the solid formed inside. Hopper inside of the drum receive the flush out solids. The hopper's position compensate for trajectory that the solids follow from the normal drum. Peripheral velocity microscreen fluent with it usually used for backwashing strainers required to avoid clogging with the backwash nozzle. Inline strainers used for the purpose will require periodic cleaning. Frequent cleaning will be determined by quality of the backwash water. Systems. Backwash system used with the Zern employ with the two header pipes. One operates continuously at 20 pounds per square inch, which will other operates at 40 to 5 pounds per square inch. Under normal operation conditions, the jets operate at 35 pounds per square inch. So today they are operated at 50 pounds per square inch for a half an hour to keep the jets free of slime buildup. Should the procedure follow to keep the jets clean, the pressure is raised to 55 pounds per square inch. At this pressure, the spring-loaded jet mouth widens to allow the more effective cleaning. Alright, high pressure backwasher pressure can be increased with the compensate with heavy siding solid loads will require high pressure through cleaning, and the superiority of high pressure systems is manifest in the following. Operation 50 pounds per square inch is opposed to 15 pounds per square inch. Increase the process with flow capacity of 30%. Solids, suspended solid concentration in the backwash can increase to 260 milligrams per liter, 15 pounds per square inch, to 425 milligrams per liter to 550 pounds per square inch. Water consumption of the jet's purpose proposed the fluent decreased with 5% with 15 pounds per square inch to the 2% with the 50 pounds per square inch. General backwashing system is operated with the low pressure possible. Consistent with successful cleaning, high pressure operation occurs added to the system. Maintenance, particular jet placement is used only as needed. Supplemental cleaning over a period of time. Same screen fabrics may become clogged with alga. slime, growth, oil, grease, algae, slime, growth, oil, grease to prevent clogging. Cleaning methods, addition, backwashing are necessary. Ultraviolet lamps reduce clogging of the algae and the small growth. Ultraviolet lamps placed with a close proximity to the screen fabric monthly with the removal of the unit screw to permit screen the cleaning with mild chlorine solution is recommended with a moist light. Literature sources says ultraviolet lights are valued 1 or 30 feet of the lamps, so uneconomical because they require frequent replacement. Hot water, where oil and grease are present, hot water and steam treatment can be used to remove the material from the microscreen. Plastic screens with grease problems are cleaned monthly at a hot water at 1200 degrees Fahrenheit to prevent damage of the screen material. The downtime into cleaning up made up to 8 hours. Alright, operation. In setting microscreen unit, care should be taken to limit the differential of water level across the fabric. Normal design range of 2 to 3 inches for the example the drum is being filled. Should be kept in rotation. Backwash water should be turned as soon as possible. This is done to limit the formation of excess of the differential heads across the screen, which would stress the fabric during the tank. Leaving the drum staying with the dirty water should be avoided because of the suspended matter of the inside screen face, which is above the water level that may be dry, but the proof of the difficult to remove for this reason. Introducing unscreened water, such as the plant overload of the microscreening effluent compartment, should also be avoided. If the unit is to be left standing with any length of time, the tank should be drained with the fabric clean to prevent clogging of the dirt and drying solid. Filterization. Basic design parameters. Basic parameters to consider are the following: type of the filter, media type of the filter, rate, duration, timing of the backwash file, filter run duration, filter rate, and typical type of the chemical pre-treatment dosage requirement. Course and media filterization. General design consideration. Filter media size of the influence filter, performance smaller media with the achieve the better of the suspended solid, removable with the increase the pressure drop and head loss piled up. Therefore, a balance between the removal efficiency, hydraulic loading rate must be obtained for the sewage application course media. Higher flow rates, longer filter runs will be used for the chemical treatment of feed water may be necessary to improve the effluent quality. Media size and filterization rate. The coarse media particles that must have an effective size approximately 1.3 millimeters. Uniform efficiency approximately 1. Sand and anthracite coal may be used with a goal given the proper pore solid to remove the butt, producing less pressure drop. Refer to the EPA process design manual for suspended solid removal. For additional information regarding media specification and the design application rate with the coarse media filters, will it be 5 gallons per minute per square foot at maximum design flow. Effectiveness. Single media with the coarse sand filters credited with up to 60% of the removal of the suspended solid sands. Media size no greater than 1.0 millimeters. Flow rate with no greater than 4 gallons per millimeter per square foot. Biochemical oxygen demand removal efficiency with dependent on the biochemical oxygen demand fraction of suspended solids with removed since the dissolved organic materials generally pass through the filter. Multimedia filterization. Multimedia filterization compared to single media filterization provide better suspended solid removal. The longer filter run with a higher flow rate, 75% of the suspended solids removal efficiency. Multimedia filterization will be acceptable to design allowance for design application rates of 5 gallons per minute per square foot. Filter age, such as aluminum, can be bathed with increase the removal of efficiency of the application of 6 gallons per minute per square foot. The maximum design flow will be utilized for the design. Typical design parameters, multimedia filterization process given in tables 3 and 4. Show the coal depth and size of mesh in inches, sand depth and size of mesh in inches, garnet size and depth in inches, dual 1, media 2, 3, media 4, and media 5. And this shows a table of performance parameters for the multimedia filterization process element of the design. Create hydraulic loading 4 gallons per minute square foot. Pre-treatment load required removal of settable solids. Depth of the filter media 30 to 36 inches. Length of the run 10 to 15 hours. Terminal head loss 6 to 8 feet. Water backwash ratio 15 gallons per square foot. Upflow filterization. Upflow filterization utilized with the pressurized wastewater feed with the pillars of the upward direction. Upward flow overcome with the fine coarse particle side of the distribution. Disadvantage single media filter. The media used with the sand on the top of the gravel. Some of the models contain with the grate on the top of the sand layer to keep the compact during filterization. Type of the filter achieved with the gravity suspended solids. Removal 85% capable of the higher solids loading of the conventional filters. Maximum design filterization rate will be 8 gallons per minute per square foot. Continuous upflow air wash filters are also available. Filter washing. All filters with the exemption of the upflow with the type of the will require the reverse flow backwash rate of the 15 gallons per minute per square foot. Increased application forward wash rate of the 25 gallons per square foot will be used. Our upflow filters Required design duration wash cycle will be 8 minutes for the source wash water. The sewage filterization application will be filter effluent, chemical colligated, settled effluent rather than secondary effluent to ensure the filter of the wash supply will always be free of large quantities of the suspended solids. Filter wash flow indicator should include so that the operator can be sure of the desired wash ratings is being maintained at all times. The wasted wash water must be reprocessed. Storage facilities will be provided with a filter wash wastewater returning process at a controlled rate not to exceed 15% of the inflow. Provisions must be made with the store of the incoming flow during the filter wash cycle. Therefore, no parallel units to increase the rate of other filters during the washing cycle. Either mechanical surface washer equipment, air scourging facilities will provide it as part of the backwashing design consideration. Alright, 6. Activated carbon absorption. Using activated carbon absorption will be based on carbon column studies performed by a waste of the type of the carbon that is being used for the operating process of the site. Proposed process configurations. Downflow. When used with the downflow configuration, carbon absorption leaves the beds accomplish filterization as well as absorption. Generally, if inefficient use of the activated carbon require frequent backwashing, feed water, suspended solids concentration greater than 50 to 65 milligrams per liter solid removal per treatment must be provided. Downflow carbon absorption profit the operator the hydraulics rating from 2 to 10 gallons per minute per square foot over the column's cross-section area of the columns must be maintained in aerobic condition to prevent sulfide formation with accomplished for the maintaining dissolved oxygen level to feed backwash waters. Upflow carbon absorption can be operated with different modes of the hydraulic using loadings less than 2 gallons per minute with per square foot. Carbon bed remains back to the bottom column with providing filterization as well as absorption. Filterization can cause a backwashing problem. Hydraulic loadings 47 gallons per minute per square foot. Carbon is partially expanded with the suspended solids path through the bed. The loadings greater than 7 gallons per minute per square foot. The carbon bed is lifted upflow with the carbon beds usually operated with expanded bed or partially expanded bed mode and normally require no backwashing. However, the periodic backwashing helps remove the carbon fine. Post-filterization will provide to move suspended solids fluently. Your pulse bed. A pulse bed is defined as an upflow carbon absorption system which layer with exhausted carbon withdrawn with the bottom of the carbon bed with a regenerated layer being added to the top of the bed. The technique approximates the current countercurrent operation nearly continuous process. Our gravity and pressurized flow. Gravity system will have an advantage of eliminating the need for pumps and pressure vessels. The restriction fracture is gravity flow. Head loss for the region with pre-treatment of solids, suspended solids removal is required. Gravity flow systems can either be downflow or upflow. Upflow expanded bed configuration will facility maintenance for the cost, and head loss pressurized flow systems will more flexible process design, operating high flow rates and over wide ranges of pressure drop. 615 series parallel arrangement. Carbon contacting beds can be arranged with a single state, independent operators, multi-stage, either in series or in parallel configuration. Achieve the more complete with the organic removal will be using carbon absorption required to remove 90% of the total plant organics. Economic studies indicate the two-stage series of operation less expensive in terms of operating costs for the lower level of treatment. The single stage parallel contractor stage and their station status of operation degree of the exhaustion can produce the desired product blending in an individual effluent. Regeneration. Activated carbon to regenerate the step heating process referred to EPA to process the design manual with the carbon absorption with the detail. The design detail of the carbon regeneration system includes the primary dewatering with the carbon slurry to a moisture content of 40 to 50% with the heating of the multi-earth 400 to 1500 to 1700 degrees Fahrenheit, quenching of the regenerated carbon, recycling to contactors. Regeneration process requires 3200 British thermal units for the burning off of the impurities, 1 pound per steam per pound of regenerated carbon. Air pollution control equipment is required, usually after burning a wet scrubber and a bag filter. Carbon transport. Carbon usually transported with the system as a slurry velocity of between 2.5 and 10 feet per second. Low velocities make with a system vulnerable to solid disposition. Higher velocity with the vibration in pipes. Velocity 3 to 4 per feet per second with 4 pounds of water of carbon to a half a gallon of water per pound of carbon as recommended. The carbon slurry can be stored before or after regeneration and can be transported directly to or from contactors. The ladder arrangement requires at least 2 spare contactors and a significant cost factor is pressurized system. Alright, backwashing. Backwashing is frequently determined by head loss buildup with lower flow rates, usually always allowing less frequent backwash, supplemental surface washing, air scoring, completing operation lasting 15 to 45 minutes. The backwash should be provided with 30 to 50% bed expansion while consuming more than 55% of the normal feed rate, 15 to 20 gallons per minute per square foot. Effluent can be used with the backwash, then returned to the preliminary treatment stage. Process design parameters. When practical carbon column studies shall be conducted only on the waste to be treated to determine the process design parameters of the study should be used with the type of the activated carbon that will be used in operating full screen plant. Pretreatment will provide the necessary to keep the suspended solid concentration below 50 milligrams per liter unless the carbon bed is used to filter. Also, carbon size will be between 80 and 30 mesh granular carbon unless the carbon column studies that show the different sizes to be more effective. Contact time. Contact time is the most important design factor affecting organic removal that should be determined empirically for a particular situation. Typical values range between 18 and 36 minutes. Hydraulic loadings. Hydraulic loadings between 2 and 10 gallons per minute per square foot are acceptable. This appears to be effective with the organics removed within this range. Main consideration: head loss buildup. Gravity flow systems are limited to hydraulic loadings less than 4 gallons per minute per square foot. Carbon quantities and absorption capacity. Carbon requirements range from 250 pounds to 350 pounds of carbon per million gallons treated with 300 pounds per gallon with the preferred value. Absorption capacity. Each of the carbon effective with severe factors determined experimentally for each particular wastewater treated. Factors influence absorption include surface area, nature of the material to be absorbed, absorber, pH, temperature, nature of the carbon absorbent, complexity of the material to be absorbed, the absorption capacity. Carbon cycle usually ranges from 0.25 to 0.87 pounds COD removed per pound of the carbon applied to obtain the guidance regarding the selection type of O activated carbon to be used the bench scale with the pilot scale studies and refer to Chapter 4 EPA Process Design Manual for the carbon absorptions. Hard equipment. The effluent quality requirement determine the required contact time and is determined the approximate total carbon volume with the hydraulic loading. Determine the total cross-sectional area with the total carbon depth. Bed depth. The total bed depth has been divided between the bed and street. The total cross-sectional area can be divided in separately carbon bed. For the parallel vessel heights should be provided with the bed expansion. 50% contact tanks should have length of the diameter ratio between 0.75 and 2.0. Carbon depth usually greater than 10 feet of the tank should be constructed with concrete lined carbon steel. The typical coating materials range from a paint, coal, tar, epoxy, laminated rubber linings. Carbon transport system must be designed to resist abrasive carbon slurry. More specifically designed details can be obtained with the EPA process design manual for the carbon absorption from equipment manufacturers. Phosphorus removal. General approach is mineral addition, lime addition principle. The method of the in-plant removal of phosphorus of waste. Most commonly used these melt salts are hydrated aluminum sulfate, sodium aluminate, ferritic sulfate, ferrous sulfate, ferritic chloride, ferrous chloride. Mineral addition usually followed with the anionic polymer addition with the aids of fluctuation of the pH may require adjustment depending on particular process addition with the phosphorus removal attained through the chemical precipitation of hydroepoxyated design with the phosphorus removal system with the consideration must be given the phosphorus level of the system of fluent suspended solids. Additional information be found in EPA process design manual for phosphorus removal. 72 mineral addition for the using aluminum requirement, theoretical requirements of aluminum and precipitating process, mole ratio aluminum phosphor 1:1. In actual case history it indicated considerably higher 2:1 skygrometer quantity of the aluminum needed to meet the phosphorus removal. The quantities with aluminum addition were worse over the pH too low for the other treatment process. The theoretical weight ratio alum to aluminum is 11:1. Practice aluminum weight ratios range from 13 to 1 to 22 to 1 depending on the degree of the removed desired. Having the need with a higher removal efficiency, A1P ratio must be increased to table 5 of the A1P or the ferritic phosphate ratio is required 75 to 85 to 95% of the phosphorus removal. The laboratory pilot plant full-scale trial runs are often necessary to determine the most effective manual dosage. So the phosphorus removal, the percentage 75%, the aluminum phosphorus ratio 1.2 to 1, and ferritic Phosphate 2.3 to 1, 8 phosphorus removal percent 85, 1.5 to 1, 1, 2.7 to 1, 95% of the removal of phosphate, 2.1 to 0 of the aluminum phosphate waste ratio, and 3.1 the weight ratio of the ferritic phosphate. In addition, with the primary treatment stage mineral added to the directly to the raw seed with the mix with adjusting the pH if necessary, fluctuated and clarified with mixed wing flocculation carried out in specially designed unit with the existing system in appropriate locations such as the manholes, bar shell, flumes, pre-aeration tanks, maximum phosphorus removal, the minimal addition of the downstream return stream, so the digester supernat the required procedure of the mineral addition with the primary stages fouls, add mineral to raw sewage, mix thoroughly, add alkaline as necessary pH adjustment 10 seconds later, allow reaction for at least 10 minutes with add ionic polymer flax mix of 20 to 60 seconds, provide mechanical air fluctuation from 1 to 5 minutes, and deliver fluctuated flocculated wastewater sediment into units. The advantage of removing phosphorus with the primary state of the flexibility, chemical feeding, adequate detention time with the mixing conditions of the available reduce the suspended solid of the biochemical oxygen demanding loading of the ensuing of the secondary treatment stage, easing process and instrumentation. Principal advantage: the significant portion phosphate of the orthophosphate with the form of the primary treatment stage, therefore does not precipitate easily. Mineral addition also causes the increased solid productions of 1.5 to 2.0 times the weight of the normal primary solid with the solid density, increase with the aluminum dosage. Solid increase attributed with aluminum addition of about 4 pounds per pound of aluminum added stoichiometer proportions after with the weight gain is less. Additional aluminum with the primary stage generates large quantities of the metal hydroxide sludge, which is difficult to dewater. In addition to secondary treatment stage, advantage of the mineral addition with the activated sludge process with the enhanced sludge removal properties, shorter residence time, more effective phosphorus removal before because of the sludge recycles with relatively small additional solid production, which improves sludge and density and dewatering flexibility charging conditions. Extra solid production, however, does involve additional sludge handling just as the aluminum is added to the primary stage, and the activated sludge product with the chemical is added near the discharge point with the aeration basin mixing with the chemical wastewater most occur with the basin with the premature precipitation must be prevented. Phosphorus capture will occur primarily with the sediment units following the aeration and the basin following trickling filter plant, and it can be demonstrated the precipitation final clarification both effective and controllable as per EPA Manual 670 273-060 orthophosphate predominance point with the precipitated readily well. Also, biodegradable detergents interfere with the precipitation largely absent underflow solids from those final clarifier return for the primary clarifier result of the unusual effective clarification operation not done effectively. Poor treated effluent can escape the receiving the water in order to allow incorporating the advantage of chemical treatment, both primary and secondary clarifiers provision. Future installation chemical addition mixing facilities provided with the primary clarifier facilities provision mineral addition of both primary and secondary clarifiers provide for flexibility operation. Chemical treatment of both clarifiers can be used with experience, but shall be most effective technique of the particular plant involved. Initial equipment will be provided only with a secondary clarifier unless potentially pilot plant operates show more effective performance at another location shows the necessity chemical feed with the primary clarifier as also. Alright, pH. The optimum pH precipitation with aluminum is weighted is about 6.0 with a degree of the operating pH range. The activated sludge process, which makes the phosphorus removal during activated sludge treatment are very effective with interfere with the slightly nitrification and optimum pH range 7 to 8. With both nitrification and phosphorus removal, the desire to accomplish a single process with such extended aeration and nutrient removal, efficient accomplished with a pH about 7. Velocity gradient. So the velocity gradient is determined with equation 1. G, the velocity gradient in seconds to the negative 1 is equal to the power requirements of foot-pounds per second over the absolute fluid vessel of the pounds per 4 square inch by the fluctuator volume cubic feet. The velocity gradient is 75 seconds to the negative 1. Will cover the sum of the flow disintegration that usually exceed the typical aeration basin. Achieve better settling, therefore more effective phosphorus removal of the general mixing provided towards the end of the aeration basin flocculation chamber. Our weight ratio for combined chemical biological phosphorus removal system weight rate with the net with volatile solids with the aeration-based aluminum adds with the most succeed with the API aluminum phosphorus weight ratio not less than 3. From the occurrence of the non-settable and solid suspended solid with the fluent with the aeration basin. More biological solids produced through the system, greater aluminum dosage that can be used without fluent suspended solids problems. Mineral precipitates, in general, sludge contain mineral precipitates, phosphorus that are stable to sludge digestion, heat treatment. Phosphorates as well insoluble hydroxide. Excessive minerals do not resolve. They have no detrimental effect of the digestion process. Additional final settling basin. The final settling basin phosphorus remove the effect of the because the most soluble phosphates are in the orthophosphate form. Easiest precipitate. General procedure for mineral addition. Essential same in the primary stage. Surface overflow rate with 500 gallons per day square foot should be the size of the final settling basin. Mineral addition using iron. Iron requirements. Theoretical requirement of iron phosphorus. The precipitation in terms of the mole ratio of the item to ferrous as 1:1 ferric iron. 3:2 ferrous ion. Actual plant results indicate the mole ratio of the ferrous ion closer to 1:1. The same mole ratio of ferrous and ferric iron. The weight ratio of the ferric is 1.8 to 1. Aluminum, however, the experience indicated the weight with the ratio higher. Optimum pH range with the ferric iron precipitation phosphorus is 4.5 to 5. Ferrous iron is about 8. Pure salts cause lowering pH may necessitate the addition of alkaline. However, the alkaline addition is necessary to accept that there is a subsequent aeration step. Alright, effectiveness. The addition of ferritic forms of the iron tends to yield a fine light flock that does not settle well with a subsequent addition with lime and the polymer aids flocculization. Settling of the ferrous iron addition may present residual problems in that excessive ferrous irons may not hydrolyze, settle out with a pH lower than 8.0. Lime addition, raising pH all to alleviate the problem. The ferrous salt yields good result. The oxygen available to such the activated sludge process. Ferric and ferrous iron addition together, lime and polymer flocculization aids. Particular application of the primary treatment of the subsequent activated sludge step because there is a little affluent flow carry over the milder insulation is preferred with the chemical additional flow for biological reactor. Mineral addition treatment scheme pilot plan study with a full scale of the plant operation to the most effective practical treatment scheme for particular situation. The most often involve the multi-point chemical addition with the recycled mineral sludges and cave with the trickle filter plant. Mineral addition with a split about 20% of the primary stage, 80% of the final clarification with the sludge recycle from the final settler preliminary settler process provides very effective phosphorus removal with good clarification. When removal requirements permit 5 milligrams per liter more phosphorus than the effluent stream required. Treatment will flow trickling filter, very high phosphorus removal efficiency, multimedia filterization added for the secondary settling. Mineral selection and dosages, cost and availability. Choice of the minerals should be based on the cost of the materials available. The materials process performance, cost, availability will determine each particular situation. Aluminum and iron salts are made the same cost range. Aluminum salt somewhat more expensive. Side effects of various minerals. Both aluminum and iron additives will produce soluble side products for the form chloride, sulfate, sodiums, compounds, as well as free acids, alkalines, due to the hydrolysis. These sides of the product seldom with a serious problem, however, that can be controlled by adding on the proper amount of chemical throughout the use of the automatic monitoring instrument. Aluminum ferric chloride are most commonly used with mineral salt. Both the cause of the alkaline drop the kind lower below pH 3, buffering capacity not adequate as iron tend with a yet higher influence residual amount around 6 milligrams per liter is for iron. Then aluminum is 0.5 milligrams per liter of aluminum. Aluminum addition produces 30 to 50% less additional solids than iron additives. The sludge has greater dewatability sludge density. Aluminate and aluminum produce about the same amount of sludge, with aluminum sludge is considerably less dense. Aluminum addition tends to produce better effluent clarity than does aluminate. Are determined the doses. Mineral doses will be determined by the weight ratio of the applicable. The pilot plant laboratory study full scale plant test runs. Aluminum doses usually range from 150 to 250 milligrams per liter. The average influent phosphorus concentration of about 10 milligrams per liter. Typical iron dosage range from 10 to 25 milligrams per liter as iron. Typical dosage will accomplish 80 to 90% phosphorus removal. The greater phosphorus removal, the down the residual less than half a milligram as phosphorus can be obtained using multiple media filtration techniques for the EPA process designing of phosphorus removal. Lime treatment process description: condition lime addition accomplished with phosphorus removal, the chemical precipitation hydroxapate. Although soluble product theoretically determines the amount left of the solution, actual determination factor, removal efficiency, clarifier, precipitation of phosphorus by lime requires high alkalinity if pH for being 11 being optimum. For lime doses, not the function of phosphate concentration, rather depends on the amount of lime necessary to attain proper pH. The term largely dependent on the influent wastewater alkalinity, which is illustrated in Figure 2. Typical lime dosage as much as 400 milligrams per liter as carbon CaO necessary to attain pH 11. Are the advantages of the lime treatment: phosphorus removal, the lime addition of these advantages, no soluble side products that improve the oil, grease, and scum, the removal of less corrosion, sludge handling system, recovery of the lime, and the disadvantage of the high pH required for the lime addition, the detrimental effect on downstream biological treatment process, including activated sludge trickling filters and sludge digestion. Hard treatment configuration. Lime treatment can be either single stage or two-stage process depending on the degree of the phosphorus removal required for the alkalinity of the wastewater. Low alkalinity of the 150 50 milligrams per liter is the lime will yield poor settlement flock. High alkalinity requires subsequent recarbonation. CO2 contacts lower pH will turn the calcium trichlor CO3. Precipitate requires high secondary stage of the calcium CO3 sludge. Provide better clarification of high alkalinity, 200 milligrams a liter of the calcium CO3. Other on hand yield the good settling flow at pH as low as 9.5, eliminating the need of second stage since CaCO3 precipitate will come out of the first stage process will be 3, and consider the alternative when using mineral salt will not be satisfactory. Alright, feed water alkalinity versus lime dosage. Lime dose for feed alkalinity milligrams. Single state lime treatment. The general procedure for the single state treatment is as follows: add lime slurry to wastewater and either retain the 9.5 to 10.5 pH. Provided rapid mixing for about 30 seconds. Provide flocculization, sedimentation, recalcination, and used in thickening sludge to 8 to 20% solid, potential few 30-40% solid. Then realkaline calcium with oxygen, calcium, oxygen, hydrogen 2. Usually not economical for smaller insulation after sediment. Recarbonate for about 15 minutes to obtain the pH necessary for subsequent treatment of the discharge. Two-stage limited lime treatment. For two-stage treatment, the procedure is as follows: add lime wastewater needed to obtain a pH equal to 11 to 11.5, provided the mixing about 30 seconds. Provided flocculization, settling sludge can be recalcinized in a single stage. Recarbonate with 5 to 15 minutes above the 10 to obtain the pH from 9.5 to 10. Provide second staging sludge calcinide and is required. Again, to recarbonate in about 15 minutes to obtain the pH required for following treatment, ordinary discharge. Hard effectiveness. Lime addition primary treatment stage is effective at removing the 89% of the phosphorus, also reduce the biochemical oxygen demand with a 50 to 70% suspended itself with the 85 of the nitrogen and about 25% of the coliforms as per 99.9%. However, the high pH necessary for the type of the treatment causes the difficulty downstream biological treatment processes. Neutralization, recarbonation may be required for before biological treatment. Pre-lime treatment will reduce the organic load. Secondary treatment stage will reduce the secondary sludge almost half the primary sludge. However, will increase about the 3-fold. With lime treatment, the primary treatment stage of the recalcinization often impractical because of the calcium carbon O3 may not precipitate insufficient quantity, but that more effective than flexible technique of lime addition separate stage after secondary treatment. The advantage of their flexibility, operation, backup function of the secondary system, either single stage or two stage lime treatment can be used. However, the two stage treatment is preferred because it produces better clarified effluent, has more lime recovery potential by its higher phosphorus removal efficiency, mixing focalization, settling unit separate with the integrated unit. The integrated type unit with the upflow clarifier works well, but sludge blanket problems are encountered in integrated units that work without sludge blankets. Separate units are recommended. Alright, lime addition treatment scheme. Lime addition primary treatment that can be used with an existing process. Human that separate human that can be used with modifications such as sludge, recycle, focalization, chambered polymer addition, improves settability of the sludge, and thereby improve the phosphorus removal efficiency. Mineral addition can also be used after primary treatment with lime that improve overall phosphorus removal efficiency. For additional information for the EPA process design manual, phosphorus removal. Our performance and dosage criteria. Lime requirement can overvary with the wide range depending on operation, pH, water consumption, alkalinity, effect of the lime dose for the calcium hardness. For the one part of the weight of the calcium carbonate can react within 0.89 to 1.79 parts bicarbonate. Alkalinity expressed for the calcium carbonate. Lower value with applying to the very soft waters, high value with the very hard waters. In addition to the reaction time, reaction of lime and hardness, the other competing reactions occur in lime treatment. Wastewater, although the most incomplete reaction of the lime, the complication must calculation loss and then most difficult. Consequently, determination of lime dose is largely empirical. Some of the approximate values are given in the U.S. EPA process design manual. Phosphorus removal lime dose will usually be in the range of 300 to 400 milligrams per liter. Calcium oxygen or two-stage treatment for up to 150 to 200 milligrams per liter with single-stage treatment is satisfactory. R769 recarbonation. The subject is discussed in detail. EPA process design manual. Phosphorus removal. Alright, land application system background. The use of the land with the biomass growth, the use within the soil with long, interesting history. The history, as well as much more detailed treatment of lead and application wastewater is covered in EPA 625-181-013. Should be noted with the discussion and with the supplement of the U.S. EPA manual with the detailed design criteria. This has been done because of the broad side of the specific design condition of the existing land application system. Health has regulatory limitation because of the land treatment of the wastewater that entail with a higher risk of the other treatment of profits introduced with the pathogenic microorganisms, the toxic chemicals into groundwater with the land treatment system design must carefully consider all possible domains to prevent water supply contamination. Additional state and local health regulation often dictate with the lead in land treatment the profit design criteria. Therefore, these regulations must be consulted early in the design phase frequently throughout the construction operation to ensure consistent compliance. Our treatment capabilities. Objective of land treatment of the domestic wastewater that undergo the secondary treatment of the sludge of the wastewater of the treatment plants may involve one of the following modes: land treatment of the wastewater with the primary treatment, acceptable isolated location, restricted access with limited crops which are not directly human in consumption, slow rate filterization, rapid infiltration, overland flows, use of wetland, subsurface incorporation. Two methods of land treatment applied to sludges, composting, and land spreading, subsurface incorporation. Our slow rate process essential mean irrigation of the crop of the grasslands, forest lands based on the domain of the vegetation. Typical application method involved in the pipeline of row crops, for the distribution along with furrow of the ridge of the contour, spring irrigation, drip irrigation, spring drip and irrigation, and require wastewater that is quite free with solid suspended matter is air within semi-arid areas. Utilization of such wastewaters, even only with a recreational area on a military compound, should be seriously considered both conservation and to improve the local aesthetics. Rapid infiltration off the called infiltration percolation involves almost complete saturation of the soil column, potentially also of the rock beneath it. Thick and sandy, Golith, low water table is required. Freshwater water wells, well points, springs must be sufficient far away to the most not to receive contamination. Often the objective to renovate the water to recapture the effluent gain. Special wells, under drains, reuse, and cooling integration. Rapid infiltration may be also used to prevent intrusion. Saline water in a toll with a sandy coastal plain skylight. Although vegetation utilization is not plain with a rapid Information system study that have shown the use of the date-eroded plants, active root humus mat, and total vegetation, which improve the quality of the recovered water. Vegetation must be careful. Selective the course, some of the waters must be less of the evotranspiration to production. The biomass of the living filter will produce the excellent quality water beneath the surface. Overland flow. The process involves the subsurface phenomenon that depends on the strongly vegetation myriad organism. The humus layer of the slope field, the wastewater is applied with the upper reach of the slope area is carefully constructed to match the contour of the land runoff after the source of the flow of the collected and ditches of the application may be laying or pipeline sprayers, plastic tricycle irrigators using rotate sprinklers over the land flow can be used with the forest land with a produced forage like biofilter concept. Such systems not only remove the suspended salts, kill pathogens, lower biochemical oxygen demand, and dramatically lower levels of nitrogen and phosphorus. Are natural wetlands. Although true wetlands occupy 3% of the U.S. land with surface, there is area with a great potential for recharging water table, refurbishing wastewaters, purpose utilization, ecological complex habitats, and new with the modern man began to recognize the route 19th of the depression, saltwater marsh with the swamp with the bogs, cypress stone with the sand strands could be provided excellent, very inexpensive treatment with proper system management and design. Wetlands can be treated with wastewater without damage of the existing ecology. In fact, with a nutrient added addition can enhance productivity, increase the wildlife overall aesthetics value during the cold period. Wetlands cannot handle the discharge, therefore the storage in lagoons is necessary for the loading capacity to be estimated about 40% per acre. Artificial wetlands have been constructed on a solid sandy soil using in previous plastic liner. Others have been made of less pervious silt and lined with clay. Peat bogs have been very successfully used in Minnesota and Europe. Deep swamp, neutral, artificial water, hyacinth and duckweed, wolfia, other aquatic plants have been used to remove the nutrients from the wastewater limitation. Such vegetation techniques have been placed at 35 degrees north latitude. Our subsurface application, basically the subsurface system involve either the solid mound subsurface filters. Such systems are used with adverse soil conditions exist on a high water table. Relatively impermeable clay, rich soil with shallow bedrock composition, sludge sufficient and expensive biomass is available. Spark, wood chips, sawdust, other agricultural waste sewage may be directly mixed with the organic matter, composted on new open windrows to ventilate with the building. Such products require with a greater deal of biomass, but biomass may be derived in the sun, mechanically turning to reuse the soak of them up of the sewage, more sewage. This system may be used only as flows are small. Composition must be successfully between the use of sludge and any of the unit's operation discussed in the manual. Composition techniques developed in China and India in ancient times, rediscovered in Europe in the 1800s, recently have been utilized in the United States. Moisture control. Sludge may be composed with additional organic matter the general to moisten some of the bulky organic matter, such as the organic portion of the solid waste should be used to blend with the sludge chipped media to the entrain air soak up moisture. Moisture content should keep kept at around 65 to 72%. Alright, techniques. The easiest lesson explained from the composting technique involved using partially dried recycled compost, some of the new bulking agent sludge mixed with the front end of the loader, mechanical mixer to correct moisture content. The compost was withdrawn with a turn inside out and outside in, several times in about once-a-month intervals. Even simpler techniques involved with collecting leaves and other biomass during the year, plowing the bulk agent in the windrows, pouring sludging into the depression, shovel the long length of the windrow. Some simple techniques and 6-month garring method period will assure that sufficient pathogen kill to allow use of compost on military space, shrubs, lawns, or parks. The most elaborate scheme that has been developed at Bellsville, USDA. In the system blowers aeration pipes and usually has a roof building, allowing more rapidly curing, more continuous sludge processing by the system on the 2.5 dry tons of sludge may be composited per acre, including space for building off the runoff control, adequate landscaping before any composing technique use. The belt of trees should be established surrounding the work area with order control. Proper composition is minimal. Dust dampening and seclusion. Partially finished compost combined with the fresh sludge have been treated with earthworm stabilized compost even more rapidly. Earthworms can be removed from the compost by drum screening, but both on military posts. The main function would be to speed up the sludge stabilization, produce an easily handled granular soil amendment, for which had been previously been noxious slurry. Alright, land spreading of sludges. Soil biota is capable of stabilizing most of the organic waste, including oil sludge today. Only 25% of the sludges are spread on land. Even less are composted. However, the organic materials in sludges are beneficial for restoring fertility to the soil. The distributed in the mining, graveling operations, or poor agricultural practices. However, there are some major limitations. Concentrated sludge of the non-most other stabilized placed on the land should be immediately covered to prevent odor production and insect breeding. Sludges may be slightly injected into the soil indistillable using special equipment. Deep snow and the deep frost will stop land spreading operations. Although heavy metal concentration, some say the industrial sludge have been prevented agricultural use. Limitations should not apply to the waste sludge. Is particularly useful to design sludge land disposal. Is EPA Report 625-177-008. Nitrification process description. Nitrification occurs in two steps. First, NH4 is converted to the NHO, nitrosomian bacteria. NO2 is converted to NO3, the nitrobacteria. Process limited and relatively slow growth of nitrosomians. Following this is mainly applicable to the activated sludge process of nitrification. Additional information may be found. EPA process design manual for the nitrogen control. Alright, single stage nitrification and nitrification utilize the activated sludge process design. Single stage longer detention time, 12 to 24 hours, is compared with the usual 2 to 8 hours necessary for the aeration basin in order to provide an effective microbial population interrupt. This is interpreted as mean solids residence time, which is SRT, that defines the amount of the mixed liquor and volatile suspended solid under aeration in pounds divided by the sum of the suspended solids wasted, suspended solids lost in fluid in pounds per day. The mean solid residence time will be maintained at 10 to 20 days or longer, depending on the temperature of the term of the hydraulic detention time, 12 to 24 hours. Typical temperature has a significant effect with the nitrification reaction rate. Approximately doubles every 10 degrees Celsius. Rise the temperature between 6 degrees Celsius and 25 degrees Celsius. The minimum dissolved oxygen level is 1.0 micrograms per liter, sufficient nitrification. However, the sensitive dissolved oxygen concentration critical parameter of the aeration system will be designed to provide residual dissolved oxygen 2.0 milligrams per liter, pH 8.5 using lime addition. Nursery optimum pH has been determined and reported 8.4. Lime requirements vary. The temperature must be determined by each case. Nitrification consume approximately 7.5 milligrams per liter alkalinity per milligram per liter ammonium nitrous oxide. Effectively toxic substance nitrification that can be inhibited with certain toxic substances with a halogen substitute with a malonic compound with aereo and the derivative of the halogenated solvents, heavy metal cyanides, phenyl, cresol. These, however, are usually associated with industrial waste. Alright, design criteria for single-stage nitrification. Activated sludge extend with the aeration process. Design of the single-stage nitrification system will provide increased aeration tank capacity, additional aeration to maintain the dissolved oxygen level at 2 milligrams per liter. Hydraulic detention time 12 to 24 hours. Sludge handling equipment suited light and poorly compacted sludge with a recycle capacity of 150% average flow. Food to microorganism ratio less than 0.25 pounds biochemical oxygen demand per pound of mixed liquor, volatile suspended solids. Sludge retention time period during the winter conditions in excess of 20 days, and lime feeding equipment to provide alkalinity rating from 7.5 milligrams per milligram per liter of ammonia oxide and pH between 8 and 8.5. Separate stage nitrification. Separate stage nitrification. Simply separate the nitrification process from the activated sludge process. It says a typical system in the illustrated figure 3. The main advantage of the system is allow the individual optimization activated sludge nitrification process in terms of hydraulic organic loading relationship between ammonia removal rate and mixed liquor, the volatile suspended solids concentration shown in figure 4. This little sludge waste, the separate nitrification system of sludge title sludge recycled to be used. Detention time will be between 3 to 5 hours based on the influent flow with the clarified overall rates between 500 and 800 gallons per day per square foot. Diffused air will be supplied at approximately 1 standard cubic foot per minute per gallon of wastewater treated. Nitrification trickling filter plants. Low biochemical oxygen demand loadings of less than 5 pounds per day per 1,000 cubic feet. High wastewater treatment at 20 degrees Celsius or higher are necessary. Good nitrification at 80 to 90% of the trickling filters, although they are often ran at 12 degrees centigrade. Some of the loss over the efficiency trickling filter filtered where the plastic packing can obtain 90% of the nitrification. Secondary effluent is loading rate is 0.05 gallons per minute per cubic foot. Years of not-round nitrification facilities must be designed the lowest wastewater temperature of the expenditure of the winter months. For instance, the required filter volume will be much greater than required seasonal nitrification, will require at least 2 stage treatment. Rotating biological contactor of the nitrification unit. 90% of the nitrification can be accomplished by UV. The rotating biological contactor can fluent biochemical oxygen demand less than 150 milligrams per liter. Hydraulic application rate is 2 gallons per day per square foot or less. Further information consult EPA process design manual for nitrogen control. And it shows a separate stage nitrification, and then it shows the nitrification tank loadings. Alright, air stripping. Ammonia is the molecular form air in the gas which dissolves in water, extended controlled by the partial pressure of the ammonia of the air adjacent to the top of the water. Therefore, ammonia removal of the wastewater can be accomplished by contacting water droplets with a large amount of ammonia-free air. The process of the desorption is commonly referred to as ammonia stripping. For additional information from the EPS process design manual for the nitrogen control. Alright, denitrification, suspended growth of denitrification. Denitrification performed in a heterotrophic anaerobic organism, therefore require the organic carbon source of the anaerobic condition. The suspended growth of denitrification will provide gentle mixing with no aeration, with mixed liquor being clarified with the effluent with the aerated to provide dissolved oxygen, drive off the entrained nitrogen within the sludge is recycled to the contact tank. Methanol is the most common organic compound carbon source used, and usually applied with a dose of 2 to 4 pounds of methanol. Alright, methanol is the most common organic carbon source used and is usually applied in doses of 2 to 4 pounds of methanol per pound nitrogen removed. The dose should be carefully adjusted according to nitrate concentration, temperature, and order to affect the underdosage, overdosage, raw or partially treated sewage and sludge can be used with the carbon source but yield lower denitrification efficiency. Typical design factors or systems include mixed and liquor volatile suspended solids concentration 15 to 2500 milligrams per liter, detention time 4 hours, the clarified overflow rates no more than 600 gallons per square foot, dissolved oxygen level up to 0.5 milligrams per liter, or pH of 7, optimum pH 6.5 to 7.5, 5 minutes of effluent aeration flow, recycle 50 to 100% of the average flow. Temperature effects vary significantly, should be kept in mind when designing contact tanks since it's 10 degrees centigrade decreases would require twice the tank capacity. Alright, fixed denitrification, 50 denitrification, utilize the sludge packed column, denitrification, microbiological population, chaff of the media, surface of the sand, activated carbon, gravel, coal, plastic padding can be used. The intermediate media having shorter contact times, columns can be either downflow with the upflow configuration. Upflow columns have much longer contact times, operate at lower hydraulic loadings, but more efficient, lower temperature for this downflow column. The temperature of the engine again, is a very significant factor affecting denitrification efficiency. Typical design factors, both downflow, upflow, denitrification, given in the table 6. Fixed denitrification is capable of nitrate removal efficiencies over 90%. However, the efficiency of the overall nitrification denitrification process is limited by performance of the nitrification system around 90% of the nitrogen removal. So the typical parameters, downtime and downflow and upflow. Contact 5 to 10 minutes, fine media, 1.5 to 5 2 hour upflow. Hydraulic loading, downflow 7 gallons per minute square foot, upflow 0.4 gallon per minute square foot. Media size 3.4 to 5.45 millimeters diameters. Methanol dose rate 1.8 to 1, 2.7 to 1. Moles methanol is moles N 2.4 to 1. Dissolved oxygen level of 1.0 to 1.5 milligrams a liter. Column depth 10 feet, fine media 6 feet, 10 feet, upflow 14 feet, coarse media. Alright, 3-stage biological system. The 3-stage biological essential of the decombination, separate stage, nitrification, denitrification, advantage of the system, flexibility, operation, main advantage of the capital call for the ball, the configuration, also work with the short circuiting, which could be the problem of nitrification, denitrification. When plugged, the flow does not achieve specific design factors, same as for an individual process involved with the 3-stage biological treatment can achieve the nitrogen and flows the overall 95%. Anaerobical contact process, further development at a high rate with the digestion process allowed for the separation, recycling, the digested sludge solids like activated sludge profit detention, mean cell residence times are controlled. Denitrification within these contact vessels approach 95%. And then so you have your three-stage denitrification, high-rated activated sludge, carbon, carbon O2, nitrification, NH3, nitrogen O4, denitrification, nitrogen to nitrogen, open tank denitrification, suspended growth column, denitrification, fine media, sand filter optional column, denitrification coarse media, and then an introduction to the introduction advanced wastewater treatment quiz.